Okay, we have here today another interesting integral from the UNSW Integration Bee 2020. This was semifinal round 1, problem 3. We have the integral from 403 to 405 of this whole thing dx. Okay, now some people are going to recognize this right away, but what I thought was interesting is they really kind of disguised a problem that we've seen a lot, that I've done a lot on this channel. So let's look at the really common version of this that we see a lot, which is something like 0 to pi over 2. Then we could have sine or cosine here to the nx, some exponent, but then we'll have the same thing here, sine to the nx plus cosine to the nx, where in general it doesn't really matter what n is, just as long as they're all the same. And then when we have this integral, we can use King's principle. We can do it in like 2 seconds because it's always going to be just pi over 4, but we can do it out with a substitution as well. Now what I want to do to make it more clear that this is similar to this, so what I can do in rewriting this, if I use the complementary angle formula, sine of x, I can write as cosine pi over 2 minus x. So if I change my sines and write them as cosine pi over 2 minus x, and then we'll do this one in the denominator the same way. Well, now this is starting to look more similar to this because we have all of these functions are the same. We have everything cosine, the same way we have everything's natural log here. And now in our integral, everything's written as a square root. But that's just a 1/2 power. So still we have all the same function. We have all the same. So like we have here, it's just our n value is 1/2. So we still have all the same exponent. Now, what about this 20/20 stuff and this 12/12? What's going on there? Well, coming back to if this is our more familiar example and we just label our bounds a and b, well then a plus b is pi over 2. I could take this x. We could just write this as 0 plus x. But then at that point, you'll just notice the difference between 0 and pi over 2 is just our a plus b value here and here. And so with a substitution, we go from here to here and reverse the sign on the x. Well, it turns out the exact same thing is true here. So if we look at our a plus b value here, just labeling 405 as b and this is a, well then a plus b is going to be 808. But if you take 808 and you add it to 1212, you get back 2020. So the exact same substitution, the exact same thing that works here is going to work on our integral here. So now at this point that we see that everything is set up the same way, we could just jump to a solution, but I'm going to still go through the steps and then we'll see how it works in the end. Okay, so we'll start with a u substitution, just using our a plus b value that was pi over 2 here. Our a plus b value is going to be 808 minus x. We can rearrange this and write it as x equal to 808 minus u. Take a derivative, dx is going to be just minus du. So then we'll go ahead with this substitution. So then we'll take our 405 and plug it in, where we'll plug it in here for x to get our u value. So this is going to give me 403 here. Plugging in 403, this is going to be 405. Next, updating our numerator. If you plug in 808 minus u in here, you're going to get natural log of 12 plus x. Then this is the same thing over here, so we'll just copy down the exact same thing. And then for this one, when you plug in 808 minus u here, you get the 2020. So you get back this 2020. Sorry, I'm confusing my variables. This should be a u right here. And this should be a u right here. Let me just rewrite that, sorry. And then for our dx value, we'll just rewrite that. That's going to be minus du. But then from here, I'll take my minus sign here, bring it out front and use it to swap the bounds. Okay, so we'll put this back to 403. We'll put this back to, now it's matching what we had here. Then for my next step, what I want to do is I just want to do a variable change. So I was getting ahead of myself changing the variable to x because that's what I wanted to do. So we have everything in u, but because it's a definite integral, I can do a variable change and change everything back to x. So I'm just going to overwrite everything and put it all back to x. But what that allows me to do, if I just label my original integral I, and we label this integral I can add this one and this one together. So we'll get 2 copies of the integral. We have the same bounds here. So this is going to be 403 to 405. Notice our denominator is the same, just in a different order. Okay, so we can add these together and combine it into one integral. So now let's add the numerators. So we're adding this one here, natural log 2020 minus x. And then we're adding it to this one. So this one's going to be natural log 1212 plus x. And then here we see the reason why this simplifies so nicely is because we've got the same numerator, same denominator, everything cancels out and it just leaves 1. So all we need to do is integrate 1 in order to finish this off. So we integrate that, we get x evaluated from 403 to 405. Then let's finish it over here, remembering that we got 2 copies. So plugging in 405, we're going to have just 405 minus 403. We want to divide by 2 so we can isolate just 1 copy of the integral. Divide by 2 on the right. 405 minus 403 is 2 divided by 2, and so our answer is just 1. And then just going back to why I said you can do this integral in like 2 seconds from the beginning. Well, if you see the whole pattern and you know that everything here is going to be just 1, well then you're integrating 1. You can go basically right to this step. 405 minus 403 is 2, but it's going to be 2 copies, and you just have 1. Okay, so there you have it, an interesting problem with the King's principle. Thanks everyone for watching. Have a good day.